it's always a bit tricky together with the glasses, but I will manage. Yeah, this is fine. This is fine. Okay. Yes, sure. So everything is recorded, right? Yeah, wonderful. Because otherwise I would have asked whether someone will take notes, because I was asked by one participant who will only come today whether someone could take notes. But okay, so thank you very much for the invitation. Thanks for coming. And this will be the lecture series in 3 parts on Quivers and cohomological Hall algebras. I'll write it with a capital C, cohomological Hall algebras. Okay, so this series of talks will be purely from the mathematical side. I will try to give kind of a motivation from the physics side, which I actually don't know. Yeah, so this is really just about the mathematics. And let me start with motivation and aim. This is part 0 of my talk. So the motivation is a bit, it's very, very sketchy. Because I will not be able to motivate what I will be doing from the physics perspective, because I just don't know it. But I will give you a brief idea of where the things which I'm doing, cohomological Hall algebras of Quivers, originally come from. So this starts in 1996 with a paper by Harvey and Moore, which was called Algebras of BPS States. So that's the name of the paper. What are they doing? Well, they are defining an algebra. Let me just write down something and then explain the individual things happening there. So this is an object A. This is an algebra. So what are these things? The M gamma is a series of moduli spaces. So in their setting, it's certain moduli spaces of sheaves on Calabi-Yau threefolds. Everything which I underline, I will explain in the following, in this series, in my situation, Quivers. So we will learn what moduli spaces actually are mathematically, yeah? Because they are not so easy. They're easy to define in the physics literature, but to make this mathematically precise isn't that simple. Okay, so this is a series of moduli spaces graded by some gamma. This is a charge lattice often. Okay, a series of moduli spaces. And then you are taking some cohomology of these moduli spaces. A suitable cohomology. And we will see which cohomology to take, because that's also a very delicate choice mathematically. It's great to have so many colors around. And okay, so then we just take the series of moduli spaces, we take the series of the cohomologies, we put them all together with this direct sum. And on this thing, we will now have a product structure. So, comma, star. So this is a product. Yeah, okay, so the arrows are a bit messy, but it's fine. So this is a convolution product, and I will show you what convolution products are. Convolution product along a correspondence. So, and the magic of this is you define such a convolution product structure on cohomology of a series of moduli spaces, and automatically you expect something wonderful to happen, some very, very interesting algebra to arise. Yeah, so this is the ultimate aim, an interesting algebra. So this is an interesting algebra. And we will indeed see that this is very interesting in the examples which we can calculate. So this was the promise of Harvey and Moore from 1996, and mathematicians struggled with this paper because none of these things really worked mathematically. Yeah? Physically, they were all fine, but mathematically, no, it just didn't work out. Until 2010, Kontsevich and Solbermann made a suggestion how to make this precise. So, Kontsevich, Solbermann, 2010. Let's say a math version of these BPS state algebras, which they called the cohomological Hall algebra. Of whatever. Ultimately, the aim is to define this cohomological Hall algebra for sheaves on 3 Calabi-Yau manifolds. But still, it doesn't really work because, well, CY3s are quite difficult and sheaf theory on them is quite difficult. So let's first aim at something much, much simpler. Namely, let's do everything for a toy model. For a toy model, namely moduli spaces of representations of Quivers. So, for us, cohomological Hall algebras of representations of Quivers. So, and this is something I will underline. So this I will explain in all detail what the cohomological Hall algebra is, and I will explain what representations of Quivers are. And although this was originally just meant as a toy version of the actual theory you want to have, this is already extremely rich, and you can get really, really interesting algebras from that. And I would like to, and this is one of my aims, to actually do computations in such cohomological Hall algebras and enable you at the end of my lecture series to do actual computations. And I will show you the points where more computations have to be done. Yeah, so I think even very, very simple cohomological Hall algebras are not yet understood, and you can just start from scratch with direct calculations and discover something new. Yeah? Okay, so that's the list. So my list of aims is to define, make all underlined notions precise. Mathematically. And do calculations in cohomological Hall algebras, which from now on I will always abbreviate as cohas, cohomological Hall algebras. Do calculations in Hall algebras. So that's the first aim, calculations. And we will discuss some main results, main known results, and there are many more unknown results. And the known results should then really show you that indeed you get interesting algebras. Algebras. No, it's an interesting algebra. Okay. And that indeed we get interesting algebras even from this toy theory of Quiver representations. Okay, so that's the aim and scope of this lecture series. And I will try to not assume any of these notions which I wrote down there. And yeah, so first of all, we will start with Quiver representations. That usually takes some time to define because the Quiver terminology is a bit non-standard, and if you have not seen Quivers before, then you need some time to really get into this, but I will just carefully go through the basic notation of Quiver representations and show you examples so that you get a little bit of a feeling for that. So that's the first part of this lecture series that I would like to define or discuss Quiver representations. So that will be part 1 for today. And part 2 will then be the actual definition of this cohomological Hall algebra. And my optimistic aim for today is that at the end of this lecture, we'll actually write down the definition of cohomological Hall algebras in sufficiently many details. Yeah, and tomorrow we will then do calculations, because this structure is really new and we really have to get used to it. All right. So that's the plan. I haven't thought about all the material for the third lecture on Wednesday. So if you have a wish list of what I should discuss, then you can just tell me. And if I know something about this, then I will try to tell you. All right. So let's start with quiver representations. And quiver representations are just a tool, a language for formalizing problems of linear algebra. Yeah? So the first papers on quiver representations, in particular from the Kiev school on quiver representations from the 1960s and 70s, were actually called problems of linear algebra. That was the context. And by now, this is formalized in some language which is close to homological algebra, category theory, and it's this language of representations of quivers. And I will show you the basics of this language and convince you that at the end, we're just trying to solve problems of linear algebra. Really just doing things with matrices, very, very explicit. So part 1, quiver representations. Okay, so a quiver is nothing else than a directed graph. Yeah, so this is just a very colorful terminology. A quiver is something containing arrows. Yeah, you carry it on your back, and you have some arrows inside, and you get the arrows. And yeah, so it's something containing arrows, like a directed graph. That's where the terminology comes from, because Gabriel, who invented this terminology, he really liked colorful terminology. So in the following, Q will always be a finite quiver which is nothing else than an oriented graph with finitely many vertices. And the set of vertices I will denote by Q0. And finitely many arrows, Q1. And the vertices I will typically denote by, say, I. Now, this is undistinguishable from vertices will always look like I, J. And arrows I will really write as alpha, beta, gamma, and alpha is an arrow from vertex I to vertex J. So this is an oriented graph, so I always have to give you the orientation. Typical examples for us will be very, very simple graphs like this one. One vertex, no arrow at all. This will be the first cohomological algebra which we will compute tomorrow. Let's make it more complicated and have a vertex and one arrow, and this arrow is actually an arrow from this vertex to itself, which is not forbidden. This will also do. Then one arrow between two vertices. And then the most complicated cohomological Hall algebras we will see actually explicitly are, well, if you have two parallel arrows or if you have one arrow in this and arrow in this direction. So these are the examples which we'll actually discuss. But then, of course, you're allowed to do whatever you want. You can like have a parallel arrow and one back and have several loops attached here and whatever. These are typical Quivers. Okay. So, no relations. No relations. There is a deep reason why I will never assume any relation, at least today and tomorrow. There's a homological reason for that. So maybe on Wednesday I will discuss Quivers with relations coming from a superpotential, because that's a 3 Calabi-Yau situation, but today and tomorrow, no relations at all. And putting relations on everything opens up an infinite world which is completely unexplored, for good reasons, unfortunately. All right. Okay, so to any such oriented graph, I will attach a linear algebra problem, which is easily explained. To any vertex, you attach a vector space, just a finite dimensional vector space, say complex vector space C to something, and to any arrow, you attach a linear map between the corresponding vector spaces. And then you have a configuration of vector spaces in linear maps, and this configuration you want to study up to base change. That's the theory of Quiver representations. Study linear algebra configurations up to base change. Let's make this precise. Complex, and I will always say complex and finite dimensional representation of Q consists of complex vector spaces Vi for all vertices and linear maps. Complex, so C linear maps, which I always call F alpha, from Vi to Vj for all arrows in the quiver. And an arrow, as notated here, is always written with its source and target vertex, and then the linear map correspondingly goes from the source vector space to the target vector space. That's a representation of the quiver. It's just a configuration of vector spaces and linear maps. This definition alone is completely useless, but now comes the notion of equivalence of such representations. Two such representations consisting of Vi and F alpha, and another one consisting of vector spaces Wi and, say, maps G alpha, are equivalent or isomorphic, if you have isomorphisms between the vector spaces which intertwine these maps. Yeah? If there exists a bunch of isomorphisms, phi I from Vi to Wi, so these are just isomorphisms between vector spaces. We will later formalize this with matrices. Just think of invertible matrices such that the following diagram commutes. That's the formal definition. And I should write this here. Did I say thanks to the organizers for the extremely generous 1.5 hour talks, because that really gives me the opportunity to go through this Quiver notation carefully. Usually I have to really do this in a hurry, but this is really perfect. Thanks a lot. Such that the following holds. Whenever a diagram appears as follows, then it should be commutative. So let me first write down the diagram. So in other words, phi j following F alpha should be G alpha following phi I, again for all arrows alpha from I to j. Okay, So that's the datum. We have isomorphisms of the vector spaces intertwining the linear maps. All right, and this now we have to digest notationally and then practically and really understand what it means in some simple examples. Yeah. So Quiver representation means replace a vertex by a vector space and an arrow by a linear map. So then you have a linear algebra configuration, a configuration along an oriented graph. That's it. And this is nothing special. The interesting thing is the notion of equivalence, and that means the vector spaces are isomorphic in such a way intertwining the linear maps. And this is formalized here. So all the vector spaces are isomorphic. And then for every arrow, you have a natural diagram appearing. This is the structural datum of the Quiver representation VF. This is the structural datum of the Quiver representation WG. And these are the isomorphisms of the vector spaces. And so everything should be compatible. That's it. Yeah? And just note, as an aside, because we will need it later, that of course, because the phi i's are isomorphic, you can rephrase this as G alpha is phi j f alpha phi I inverse. And this looks like, if you forget the indices, this looks like similarity of matrices or similarities of linear maps. Yeah? So f is replaced by its conjugate phi f phi inverse, and that should be the G. We'll come to later. Okay, so now let's just see what this means in some examples. So you could say the ultimate aim of the representation theory of Quivers, which is usually completely unreachable, is classify Quiver representations for a given graph up to equivalence. Classify Quiver reps up to equivalence. So that's the original aim of representation theory of Quivers, which is usually completely out of reach, and that's where Kohas also will play a role. But this we'll see later. I'll have this one. All right, so first example. Let's take the quiver to be just a single vertex and no arrow at all. So this looks completely pointless, but well, it makes a point, as we'll see. So what is the classification? What is the quiver representation for this quiver? It's just a vector space. Yeah? It's a complex, finite dimensional vector space. And now you need to classify complex, finite dimensional vector spaces up to isomorphisms. Okay, and they're classified by their dimensions. So there's one discrete invariant, the dimension. Yeah? Representations are just V classified by their dimension as complex vector space. That is a trivial remark somehow, but it's very important for us because that tells us that for every quiver representation we have a discrete invariant, namely the series of dimensions involved in the quiver representations. Yeah? And that's a very important invariant, so we'll define, give it a name. So in general, we will define the dimension vector, underlined dim, or this should be boldface or blackboard, of VF, just as the sequence of dimensions of the vector space is VI. And that's the whole vector of dimensions. Yeah? Okay. And this definition is motivated just by the known classification in the trivial case. Very nice. So second example. Let's move on to a single arrow. So a representation of a single arrow is two vector spaces. Let me call this arrow alpha, and let me call these vertices I and j, of course. And then a representation is just a single linear map, f alpha. And we want to classify a single linear map up to having an isomorphism here and up to having an isomorphism here. So we want to classify single linear maps up to base change in both the source and the target space. And this is also known from linear algebra, that if you want to understand such a linear map up to base change, then essentially what you need to know is its kernel and its image, or more precisely, just the dimension of the kernel and the image, and then you know everything about the linear map. Yeah, and so from linear algebra, we know that we can do the following. You can choose a basis for the vector space Vi, which is compatible with the kernel. And choosing a basis means choosing an isomorphism. You can choose a basis for the target space, which is compatible with the image. And then you have this linear map represented by a matrix, which looks like ones here and zero everything everywhere else. Yeah? So this isomorphism of Vi to Cm means choosing a basis for the vector space. So here you choose a basis compatible with the kernel. Basis compatible with the kernel. Here you make a choice of a basis compatible with the image. That's not the whole truth. You need to choose a basis such that it lifts to the kernel. But essentially then you can see, well, this part of the basis is the kernel, this part of the basis is the image, and then the linear map here is represented by this matrix. And here you only need to know this number, and the number of ones there is the rank of the map, the dimension of the image. So that's just the rank of f alpha. So that means we have easily solved this problem. So representations of this quiver are classified by 3 discrete invariants. The dimension of Vi, the dimension of Vj. Well, that's the dimension vector, that's we already know, and the rank of the linear map. The rank of the map f alpha. With natural restrictions, because, well, the rank can be anything between 0 and the minimum of these two, for example. Huh? That's obviously. And that's the classification. That's not bad. Yeah. So from basic linear algebra, we already solved 2 theories of quiver representations. That's pretty good. Let's do a third one. And then a remark, and then we are almost done with the quiver representations. I'm pretty fast, but it's okay, is it? Yeah. Otherwise, just stop me and say details, please. Okay. Okay, so third example. Let's move on to a single loop. Huh? Okay, and that's also a theory we learned about in linear algebra. That's the theory of one endomorphism. You know, the theory of similarity of square matrices. Let's see. A representation is a vector space Vi together with an endomorphism f alpha. And we want to classify these up to what I already indicated in the rewriting of this intertwining formula. We want to classify this up to similarity, where we replace f alpha by some phi I f alpha phi I inverse. And if you just choose a basis, then it's just classifying matrices, square matrices A, up to replacing A by G, A, G inverse, so up to similarity. Okay? Now, luckily for us, we are over the base field of complex numbers for a good reason, because over the complex numbers, this is solved by the Jordan canonical form. Or whatever canonical form you prefer, but let's just stick to Jordan canonical form. So, and for good reasons, I'd like to make two little observations about the Jordan canonical form. That's why I write this here. So Jordan canonical form means we identify the vector space Vi with some Cn by choosing an appropriate basis. And there's this Jordan basis for the generalized eigenspaces. And this the endomorphism then looks like, well, first of all, it looks like a diagonal matrix, a block diagonal matrix, and the diagonal blocks are J1 to Jk, and each block, say Js, looks like a Jordan canonical block of a certain size with certain eigenvalues on it. Lambda s, and then here you have the ones on top and everything else. So this is a Jordan block of a certain size. Yeah, and then, well, these are the lambda 1 to lambda s to lambda k are the eigenvalues. Eigenvalues of your linear operator f alpha. And the sizes here are, well, we have to choose Jordan basis. Well, we don't have to go into this in all details, so that's okay. But let me make some observations. Now we have not only discrete invariance, we have continuous invariance. Yeah, so these eigenvalues are continuous invariance, of course. And continuous invariance in classification problems are called, or were called by Riemann, moduli. That's where moduli spaces come from. So that's our first hint on what moduli spaces will be. Yeah. So whenever you have a classification problem and you encounter continuous invariance, these are called moduli, and these moduli we want to later encode in a space. Yeah, but this is mathematically delicate. For example, one of the delicacies here, you can already see here, the eigenvalues are only determined up to order. Yeah? These are complex numbers. There's no natural ordering for them. And that's one of the mathematical problems, that the eigenvalues come unordered. Okay, and then you have discrete invariant, namely the sizes of the Jordan block. Size is a discrete invariant. Aha. So that's an important observation, and that was just my opportunity to talk about moduli. And let's make two more observations. So here we can split a Quivers representation into a block diagonal form. Here we can't. This is not block diagonal, but it's it's upper triangular. Yeah. So these Jordan blocks are upper triangular matrices. This will be very essential for defining the convolution product on cohomological algebras later on. So please keep this in mind. This will be important at the end of this lecture. So, and as a final remark, after these three examples, let me tell you that these two other examples, which I've shown you of graphs, these are similar to this case. Yeah? So for both of these Quivers, you get a classification which is Well, you have some more discrete parameters, but essentially it's as difficult as the Jordan canonical form. Yeah? This was solved by Reineke in 1890. So these are classical, very classical linear algebra problems. Okay, so these are similar. And finally, if you go beyond these examples which I've shown you, like this, and so on, you get unsolved problems of linear algebra. So these are unsolved in the sense that there's no known classification of all the equivalence classes. Unsolved problems of linear algebra, very simple. This is having two linear operators which you want to bring to kind of normal form with one similarity. Yeah? So you're performing the similarity operation there, but with the same phi I on both matrices, unsolved. You have three linear maps in parallel, and you are allowed to perform base change here and here, unsolved. And many people in representation theory say not only unsolved, but unsolvable. But I don't believe this. They say unsolvable because by some clever tricks of language, model theory, you can have some undecidability results and so on, yeah? So these theories are undecidable for a Turing machine, but my point of view is we are physicists and mathematicians, we are of course better than Turing machines. So it's unsolved, but I don't think it's unsolvable. Okay. Right. We need one more notion which will be essential for us and which somehow starts from this observation here. And after this notion, we can go on to geometry. So far, we have seen about Quivers representation, just the definition of a Quivers representation and the notion of equivalence. There's more. For example, what we need is the notion of a sub-representation. And I will now give you an ad hoc definition of a sub-representation, and then I will just remark that you can somehow upgrade all this to saying Quivers representations form an abelian category. But you don't really need to go into this categorical language. Yeah? So let me just define what is a sub-representation of a Quivers representation. Sub-representation of a Quivers representation consisting of these vector spaces V and these maps F. And I think you can already guess what it is. For equivalence of Quivers representations, we choose isomorphism of the vector spaces, and it should be compatible with the maps. Well, why not do the same thing here? To define a sub-representation, we look at sub-vector spaces which are compatible with the maps. So subspaces, you choose subspaces ui in vi for all I, such that they are compatible with the maps. And there's one compatibility condition you can think of, and that's the right one. F alpha of ui belongs to uj for all arrows alpha from I to j. Okay. And this compatibility makes it even possible for a sub-representation to define a corresponding quotient or factor representation. Quotient representation. So what is the quotient representation? Where we just take the vector spaces vi by ui, or the quotient spaces for I, and we take the induced maps f alpha bar on the quotient level for the alphas. And what this f alpha bar is now clear. It's the map on the level of the vi, from vi to vj, and they are well defined on the factor level because of this compatibility. Yeah, it just all makes sense immediately. Okay. And now let me just express in a very elementary way what is the abelian category structure. The essence of a category is that you have objects and morphisms which you can compose, and that's it. That's not much. Well, you can guess what morphisms of Quivers representations are. Morphisms of the vector spaces compatible with the maps. And the essence of an abelian category in category theory is that that you have sub-objects and quotient objects, and you have kernels and co-kernels, like with vector spaces and modules and representations. Yeah? So the essence of an abelian category is it behaves as modules. The essence is that you have exact sequences, and now we can talk about exact sequences of Quivers representations. So this notions of sub-representations and factor representations allows us to talk about exact sequences. Exact sequences, 0, u, v, v by u. Where this is the v. This is now just a shorthand notation. I like this color more. This is the v. This collection of subspaces is the u, and this here is the v by u. This is completely unreadable, sorry. This is the whole representation v. Much better. These here form this, the sub-representation u, and this here is the quotient representation v by u, this whole thing here. And they together form an exact sequence where this is the natural inclusion and this is the natural projection. Yeah? And the only very important observation for us is that we can, well, this is fancy language of category theory, but you can really see this in a very simple linear algebra way. We have seen in the examples that it is always a good idea to just imagine everything as matrices, just choosing appropriate bases and then viewing everything as matrices. And we can also choose appropriate bases here and see what an exact sequence is. So choosing, let me say, compatible bases. You can always imagine such an exact sequence as the following. Well, here you have some vector spaces C to the E, vector space C to the EI, C to the DI, and here the quotient then is C to the DI minus EI. And now the important thing is, well, you have many of these, is how the structural maps look like. You have a matrix, say A alpha here. You have a matrix B alpha here, and here in the middle, you have a block upper triangular matrix, and that's the essential, that's the very important observation. Because this will be very central, this will allow us to define cohomological Hall algebras. This defines a stack of exact sequences which acts as a Hecke correspondence for the convolution product in fancy terminology, but it's all just linear algebra. Okay, so now we have to get this, and then we are fine, and then we can really skip to geometry. But let's first digest this. So this u, v, v by u is shorthand notation for all these structural data, but at some point I really want to get rid of all the indices. Yeah? It's shorthand notation. The v is shorthand for the f alpha. The u is shorthand notation for the ui and the induced maps f alpha. And the v by u is shorthand notation for the quotient vector spaces and the induced maps on the level of quotients. So for the vi, I just choose a basis, so I identify it with C to the DI. And now I make a choice of compatible bases. What does this mean? Well, I make a choice of bases so that the U consists of the first EI basis vectors. Yeah? So here I have a basis V1 to VDI, and here in such a way that the V1 to VEI give a basis of that. And then you have a basis, the rest of it, VEI plus 1 to VDI, a basis for the quotient vector space. That's what you do. Yeah? You make a compatible choice of basis. And with respect to the compatible choice of basis, this embedding means just embed send the first basis vector to the first, the second to the second, blah, blah. And so with this choice, you can just imagine these maps to be unit matrix 0. And the projection here is just 0 and unit matrix. Yeah? And if you have made this choice, then your linear maps, the structural linear maps F alpha, look like, well, it's some matrix A alpha here, it's some matrix B alpha here, and here you get a block upper triangular matrix. That's the important fact. Yeah? You get a block upper triangular matrix. Okay. So I will try to leave this, this blackboard as long as possible, because we will see it in the definition of the Coha. So, that was part 2, Quiver representations. So that's enough Quiver terminology at the moment. I mean, in the course of the lectures, we will need some more Quiver terminology, but not much. Yeah, I have to tell you a little bit about the homological algebra of Quiver representations at some point, but at the moment we can all be happy just with linear algebra and choosing appropriate basis. So that was part 1. Part 2, geometry. Geometry of Quiver reps, part 1. There will be a part 2 for this later on when we actually define the modular spaces. Okay, so I would like to reformulate our guiding problem of classifying Quiver representations up to equivalence. I would like to reformulate this in a geometric way. Reformulate the classification problem for Quiver representations reps geometrically. We already know there must be some geometry behind all this, because we were talking about discrete and continuous parameters in the classification problem. And to capture the continuous parameters, we have to do some geometry, definitely. Okay, so we'll do this as follows. So first of all, we will fix the vector spaces VI. And we have done this implicitly several times. Namely, the only thing we need to know about the vector spaces VI involved in a Quiver representation is their dimension. That's the only discrete invariant. So let's just fix this from the very beginning. Let's always fix a dimension vector, underline D, and this is just a tuple di I in Q0, and these are all non-negative integers. Definitely. Okay. So, and then we can always assume without loss of generality that our vector spaces VI in a Quiver representation are just C to the DI. Okay. And so what about the arrows? The arrows are then just, well, linear maps between these vector spaces, or you could also say just matrices. Yeah? And let's encode this choice of several of the matrices in one big space. So let me define RD as direct sum over all the arrows alpha, and then I will always take the space of dj cross di matrices over C. And this is where the F alpha now lives. Yeah, the F alpha, let me indicate this here. the F alpha, the structural datum of a co-representation, is a linear map from CDI to CDJ. And this I identify with dj cross di matrices of the complex numbers. Yeah? And that's where the F alpha live. Okay, so a point in here, by definition, gives us a Quivers representation where the dimension vector is given by this D. And conversely, every Quivers representation, after choosing basis for the vector spaces, gives the point in here. So this is the universal parameter space for all Quivers representations of dimension vector D. So this is a universal parameter space for Quivers representations of dimension vector underline D. But unfortunately, it's the parameter space only before taking the notion of equivalence. Yeah? And now let's reformulate this notion of equivalence in terms of, well, we could reformulate it in terms of an equivalence relation on the space, but we better formulate it as a group action. So let me define a group, GD. This is defined as, at every vector space, I just take a general linear group. And the general linear group I just now identify with the group of invertible di times di matrices. This is, okay, this is the universal parameter space. This is, well, in mathematics, we call it the base change group. And in physics, you call either this or the restriction to the unitary group, the gauge group of the theory. And since it's not really clear, depending on the theory, whether you take the GL or the unitary group U, let me just write gauge group, but well, this is the direction in which you should think. And the gauge group now acts on RD. And now the formula for this action is very simple to remember. G dot A is GA G inverse. That's essentially the action, and then you just have to find out what the indices are. And just make the indices so that everything works. Oh, we have seen this before. Not here on the blackboard, it was here. So this is similarity. So G is actually a collection of matrices, of invertible matrices GI. A is actually a collection of matrices indexed by the arrows, A alpha. And to make sense of GAG inverse, we have to specify the arrow. So we specify the arrow, sorry, this is now really tiny. This is our usual arrow alpha from I to J, in case you can't read it. Okay, and then you put an A alpha here, a J here, and an I here, and everything works, and we have seen this on some blackboard before. So this is an action. Action. The Jordan canonical form can go. Wonderful. Okay, so yeah. Now, just one observation. This is a universal parameter space for all representations. This is an action which precisely expresses the notion of equivalence. We have seen this formulation of equivalence. Yeah? So just from the very definition, tautologically, the equivalence classes of co-representations are nothing else than the orbits of this group in this space. This is the important observation. This is the key observation. Let me go key observation. I started this a few years ago in lectures for undergrad students to write a key when it's a key observation, because this is something students always remember in oral exams, where I draw the key. So This is trivial, but very important because this is what I always answer in an oral exam. The key observation is that equivalence classes of Quivers representations of fixed dimension vector D is in canonical bijection to orbits of the group GD in RD set of orbits of GD in RD, because this action precisely expresses the notion of equivalence, and this is the universal parameter space where all potential representations appear at once. Okay, this is the key observation. So now you might have an idea. Well, you might already know somehow what will happen now, or you might have an idea. I stressed several times that what we want to have is a solution for the classification problem, or that we want to capture the continuous parameters in the classification problem, or what I said at the beginning, that we want to define moduli spaces. And after this key observation, you might have an idea how to define moduli spaces, or how to solve the classification problem. So idea, solve the classification problem by defining a moduli space MD as, well, I just take the space RD and I mod out by GD. This is the orbit space. It's an orbit space, and at first sight you might say, okay, this solves the problem because that orbit space captures the whole classification, we are done. And this is the point of view which is sometimes taken in moduli space theory. As soon as you can define a moduli space, you are done, you have solved the classification problem. But, well, there's a point to this, but somehow all the fun is gone then, because the fun is actually studying these spaces. So first of all, this space is terribly bad, and we just have to erase this definition. Yeah? Let me just show you the very first example why this is bad. Let's take the quiver Q as the one we have already seen, one arrow, alpha from I to j. And then we have already seen the classification is by 3 discrete data, the rank of the linear map and the dimension of the 2 vector spaces. Let's fix the dimension type as 1, 1, and then RD, oh, yeah, and then RD is just the space of 1 by 1 matrices, and you have an action of the group GD, which is 2 copies of C star. Well, why not? But the action is by the following: ST acts on A by T over S times A. That's a quick exercise. Just work out what is written on the upper left blackboard. Yeah? Okay, so that means you just have 2 scalars, 2 non-zero scalars acting on A. You take the fraction of the 2 scalars and you use this new scalar to delete A. You have a perfect classification of the orbits. I mean, this whole space is a line, well, a complex line, yeah, complex one-dimensional, and you have the 0 is 1 orbit and everything else is 1 orbit. Because, well, the 0 you cannot delete, but every other scalar you can delete to any other non-zero. So you have 2 orbits, and so how does the quotient space look like? RD by GD is a space with 2 points, a closed point and an open point around it. Yeah, there's 2 points, one is closed, and 1 point has the other in its closure. So this is a closed point P and a point Q, so this is PQ, and the closure of the point Q is the point itself plus P. So this is a terribly bad topology. We don't want to deal with such spaces. We don't want to study cohomology or whatever algebraic topological theory of these spaces. Well, okay, so this definition just doesn't work. Well, at least we tried. And we learned something. There are good orbits and there are bad orbits, and the bad orbits are those which are small, and then they tend to have to be in the closure of other orbits. And this is why there will be a second section on the geometry of Quiver representations, where we will deal with this problem, where we'll define these proper moduli spaces. Yeah. So our first attempt, no, just didn't work out. Well, anyway. So, but this is not at all a problem at the moment, and mathematicians found a way around it. So, slogan. So this is a slogan giving us hope in bad times, in the bad time that such a quotient just isn't a nice topological space. So instead of, so if you have a space with a group action, and if the quotient x by g is bad, in whatever sense, then you don't study its cohomology, whatever this might be, might not even well defined because the space is so bad, but, well, just live with the fact that you have a space X with a nice group action G and define a theory which does not use the quotient. And there is a separate mathematical theory for that, which is called equivariant cohomology. So the G equivariant singular cohomology of X. That's what it's called. Yeah. So we've just made this observation that forming the quotient naively as the space parameterizing the orbit is just a bad idea, because even in very simple cases it just looks very bad. So we shouldn't study the cohomology. Why do we want to study cohomology at all? That was at the very beginning of my talk in this proposal of Harvey and Moore. Yeah, take moduli spaces, take their cohomology, and define an algebra on it. So that should have been the cohomology. Just doesn't work. But let's just live with the fact that there is no nice quotient and just take something called equivariant cohomology. And yeah, now I will tell you a tiny little bit about equivariant cohomology. The great thing about well worked out cohomology theories in topology and geometry is that you never need their definition. You just need a bunch of axioms which define them. And then you just work with the axioms. You never want to work through the definition. Yeah? That's the great thing about cohomology theories. Okay, and this is absolutely the point of view which I will take here. I will not really, well, I will just tell you with one line what equivariant cohomology is. Yeah? And then I will just write down a few properties which give you the flavor of equivariant cohomology, and that's enough for this talk, for these talks. Okay, so, but okay, you get the formal definition. You do the following. Let me just write it down. It's the usual cohomology of EG cross GX. That's the definition of equivariant cohomology. Now I have to tell you about EG. Now you can completely ignore this if you don't know about equivariant cohomology. If you know equivariant cohomology, it's a reminder. If you don't know, you don't need it. EG to BG is a G bundle, a G principal bundle, principal G bundle, defined in such a way that the total space is contractible. maybe I will show you. I can't even show you a reasonably interesting example. No, okay. So it's a principal G bundle such that this is compractible. This exists for most groups. The drawback is these are infinite dimensional manifolds. Yeah. So in defining equivariant cohomology, you have to pass through infinite dimensional spaces. Okay, but we don't need it anyway. And then, well, because it's a G bundle, you have an action of G in here. Then you take the diagonal action of G on both of them. And this means factor out. So this is just take the diagonal action of G on both and factor it out, e.g. cross X divided by G, and then take the usual singular cohomology of that. At this point, I assume that you have heard about singular cohomology in some course on geometry topology. And if not, then you might skip the rest of this lecture, but you can come back tomorrow morning when I will show you the algebraic version of cohomological whole algebra where we don't need cohomology at all. Yeah, so we'll come back to the algebra. We just need the geometry for today for half an hour. Okay, so this is the definition. Some properties, some very simple properties of equivariant cohomology. So first of all, the equivariant cohomology does what it should do in case this makes sense. So, equivariant cohomology was a replacement for the cohomology of the quotient x by g in case this quotient is bad. Yeah? But there are situations where this quotient is not bad, namely, for example, if the action of g on x is free. Yeah? And if the action is free, then you can form a nice quotient, and then this quotient is a G principal bundle, and then this equivariant cohomology is what we wanted to have in the very beginning. Well, this is definitely necessary. If this wouldn't be true, the whole definition wouldn't make sense. Yeah? Okay. The other extreme to a free action is a trivial action, where the group G just doesn't do anything with X. So just a trivial action. Well, if there is a trivial action, what would we expect from the equivariant cohomology? Well, it should know something about the space X, which has nothing to do with the group G, and something about the group G. Well, and then you have a natural splitting. You can split this into the equivariant cohomology of a point tensor the usual singular cohomology of the space X. This is quite natural, yeah? If you have a trivial action, then the group and the space are totally separate from each other. So should be cohomology. It should separate the G part and the X part. It knows the equivariant, it knows the cohomology of X, and it knows something called equivariant cohomology of a point. Now, what is equivariant cohomology of a point? I will only show you two examples because that's all we need. And there are two cohomologies, equivariant cohomologies of a point, which we need to know. So for example, one interesting group is C star to the R, an R torus. Well, and quite often this is the most complicated group which we will encounter, for which we can actually compute something. Then we want to know the cohomology of this, and this is isomorphic to, let me work with the rationals. I haven't told you about coefficients in my cohomology theory, yeah? Let me just say I will always work with rational coefficients. Why do I do this? Well, I'm never sure about torsion in cohomology. There might be torsion phenomena. I definitely want to ignore them. And so I take rational coefficients. If you don't know the difference, you don't care anyway. Well, you get a Q vector space out of cohomology. Okay, so this is just a polynomial ring in R variables. And this ring is graded, so these variables all sit in degree 2. Yeah? For each rank of the torus, you have one variable, and they're completely free. So this is that one equivariant cohomology group we have to know, and the other doesn't fit here, so I'll put it somewhere else. The slogan, I don't need anymore. And okay, so the other thing we need to know is the equivariant cohomology of the group GLN with respect to a point. And this is nothing else than, well, it looks similar. You have generators x1 to xn, but now you don't consider all polynomials, but only those polynomials which are invariant under permuting the variables. So the symmetric polynomials. And tomorrow, we will have to do lots of calculations with symmetric polynomials. And so if you really want to actively do calculations in cohomological Hall algebras by Wednesday, then better look up some few basics about symmetric polynomials. For example, the main theorem about symmetric polynomials today, this evening, because tomorrow we will actually use this. Yeah? And if you have never done calculations with symmetric polynomials, you really have to get used to it. So if you look it up for half an hour or so, then you are well prepared for tomorrow. Okay, so that's the other thing we have to know. And now finally, this is all we need at the moment. Okay. Yeah. One final thing I will tell you, if let me make a vague statement. This does not change under contractions. So if you can contract the space X to something smaller in a G-equivariant way, or if you can contract the group G along a trivial part to a smaller group, then equivariant cohomology stays the same. This is not a surprise if you know what cohomology is made for. I mean, cohomology should be invariant under homotopy retracts. Yeah, just contracting a space to a smaller one. Yeah? That's what we want to do. So this is invariant under G-equivariant contractions. So this is the final point. So this was my crash course on equivariant cohomology. This is not really fair to equivariant cohomology. But this is essentially all we need to know at the moment for defining the cohomological Hall algebra. And now this I will do in the last 15 minutes, define the cohomological Hall algebra of the quiver. And then if you have seen this definition, you will say, so what? I mean, how can I ever calculate in this algebra? And this we will see tomorrow. All right. So this I need because it's somehow the punchline of the whole definition. So I've reached the aim of this lecture if in 15 minutes you say, well, I mean, this was really easy to define this cohomological algebra. I really want to make it look easy by all the facts we already know. But actually, it will not be easy. Performing calculations in this is incredibly hard, and I will give you a guideline to this tomorrow. So, okay, so now I will define the coha. This is part 3. It's a definition of the coha. So I define coha of Q, of a quiver, as, well, now I run over all the possible dimension vectors. This is my charge lattice. This is the discrete data in the classification problem. And then here I would like to write down cohomology of the moduli space. This doesn't work. So I take equivariant cohomology with respect to GD of the space RD. And now I totally trust equivariant cohomology that it knows enough about, or that it recognizes enough about the action of GD on RD so that this is something interesting. Punchline, it is not, but we'll see a solution to this. Okay, so at the moment this is just a bi-graded vector space. This is graded by the dimension vector and graded by cohomology. And one of the subtleties, which we'll only see on Wednesday maybe, is playing these two gradings against each other. Yeah? So this is NQ0 cross Z graded. And the Z comes from the cohomology. That is, of course, not true. You only have cohomology in non-negative degree, but there's a reason for this. Okay, and now we will define a multiplication. So this is with a multiplication, which goes from the theory in degree D, tensor, or times, the theory in a degree E, to the theory in degree G plus D. And I will give you the full definition modulo some facts on equivariant cohomology. So I assume you've copied this, so I can erase this because this shouldn't go. And here I write down the definition. Yeah, so we want to find a way to go from a class in degree D cross a class in degree E to a class in degree D plus E. And this will involve upper triangular matrices, or this it will involve exact sequences. Yeah? So the slogan is you perform convolution along a Hecke correspondence given by short exact sequences. That's the fancy terminology, but what it means is the actual chain of operations I will now write down. So first of all, so if you don't know enough algebraic topology, or if you don't know singular cohomology, you can just completely ignore this. Yeah? The only important thing is that I will start here with the left-hand side, and I will end here with the right-hand side. And the inner mechanism we will never see again. Yeah? If you know some topology, maybe this is fun. Okay, so first of all, in every reasonable theory, you have a Coonot isomorphism, and the Coonot isomorphism allows you to identify this with the whole thing for the product of groups and the product of spaces. This is the isomorphism. This is the Coonot isomorphism. Okay. Now this space we will blow up to upper triangular matrices, upper block triangular matrices. And now I will not give a name to this space, but just denote it by this. So this means inside R of D plus E, so that's the first indication that we will end up in D plus E. Inside R D plus E, we look at those things which are in upper triangular block form, like middle terms of exact sequences. Yeah? Okay, and from here you can project to RD cross RE. What is this projection? The projection is, forget the extension part. Just forget this part, and then you have a block diagonal thing. You have an RD block and an RE block. So this is the RD block, and this is the RE block. This is just spaces of matrices. That's nothing fancy. Okay, so, and this is just forgetting a certain vector space. This is a contraction, and this is an equivariant contraction. So this is isomorphic to the GD cross GE equivariant cohomology of this space of exact sequences. This is not 100% the truth, only 99%, but enough for the punchline somehow. Yeah? So we are contracting this extension part in upper triangular matrices. And then this gives an isomorphism here. So, okay, so then we have made the space bigger. Now we'll make the group bigger. Namely, we can do the same thing on the level of the groups. No. We can do the same thing on the level of groups. This is a group which is sitting inside the large group, G, D plus E. This is the part of the group of matrices in block upper triangular form. And this is an isomorphism. Well, because what does it mean for such a matrix to be invertible? That's the important linear. Again, it's just a linear algebra observation. What does it mean for such a matrix to be invertible? Such a matrix is invertible even only if the two diagonal blocks are invertible. Because invertibility just means the determinant is non-zero, and the determinant of a block matrix is just the product of the determinants along the diagonal. Yeah? So this is invertible even only if the diagonal blocks are invertible. And this upper triangular block is completely arbitrary. It forms an affine space. And such an affine space you can contract to a single point. Yeah? And then again, equivariant cohomology is flexible enough to not see this contraction. So this is an equivariant contraction, so you have an isomorphism. All right. Now we have to do something which is called induction in equivariant cohomology. This I haven't explained. And it tells us that we can now replace this by GD plus E cross the bigger group of the bigger space. And now it's just one more operation to end up here. Okay. Oh, I will tell you what this induction isomorphism is. Whenever, yeah, this is something I should have put in the list of some properties of equivariant cohomology. Sorry for that. If you have a group action on the space X, and in G you have a, no, the other way around. You have an action of a group H on X, and H is sitting in another group G, then I don't like H, sorry for this, it should be G prime. Then the G prime equivariant cohomology of X is the same as the G equivariant cohomology of G cross G prime X. This is the so-called induction isomorphism. This I haven't told you, but you can make sense out of it quite immediately. G prime acts on both X and on G by multiplication. So it acts diagonally on both. And putting the cross G prime here means let G prime act diagonally on both and factor it out. That's always a free action. You can always do that. And then take the G equivariant cohomology of that. Yeah? And this is isomorphic to the G prime cohomology of the original space. The isomorphism, well, you can easily remember this. You can just forget about the two G's, they cancel each other. Yeah? So this is a lower index, this is an upper index, so they cancel each other, and what remains is the index G prime, which goes here, symbolically. Yeah? And the great thing about equivariant cohomology is that this symbolic thing just works. Okay? So, yeah. Why did I do this? Well, now I can make the final step to where I really wanted to end up, namely the G D plus E equivariant cohomology of R D plus E. That was my target. And this isomorphism and this map, this is not an isomorphism, this map is called action lower star. And I just have to explain to you this, and then we're done. What is action lower star? Well, first of all, you have an action map from this space to this. Namely, if you have a group element G here and an element F here, then we are taking the quotient, we have an orbit of a pair GF, and we map this to just G times F. This is our group action. That's why this is called the action map. Yeah? We just perform our group action, GF, G inverse. Okay? And such a map, this map is proper, and then this proper map induces a push-forward map in equivariant cohomology. This is one functorial feature of equivariant cohomology, which I haven't told you, but for this action map, there is an induced map action star, which we will never use. Okay, so anyway, we have found a way of starting in the theories for D and E and ending up in D plus E. This is a diagram which you have to contemplate many times in setting the foundations for the cohomological Hall algebra. And I will tell you tomorrow morning how to never use this diagram again. But I had to go through this to show you that everything is in a way natural if you believe some properties of equivariant cohomology. And the key things in there, final sentence, the key thing in there is that apart from some natural isomorphisms, what we are doing is it's just two things. We have an action map. We have a group action on a space, and this is what we are using. And this group action on a space was motivated by linear algebra. Yeah, because the orbits were the equivalence classes or the similarity classes of representations. That's why this action map is inherent to this theory. And the other thing inherent to the theory was upper triangular matrices, which came from subrepresentations and quotient representations, or in other words, from exact sequences. So there are just two ingredients for the cohomological Hall algebra. You need an action map, and you need a set of exact sequences. Yeah? And the rest is standard machine on equivariant cohomology. Why do I stress this? Well, I stress this because it tells you if you want to invent a cohomological Hall algebra in some other theory than Quivers representations, go for it. You just need two ingredients. You need a notion of exact sequences or a notion of sub-objects and quotient objects, and you need a parameter space with an action. If you have these two ingredients in whatever favorite theory you have, you can define a cohomological Hall algebra. You can define it for Quivers representations, you can define it for sheaves on 3 Calabi-Yau's, you can define it in whatever theory you like. Yeah? Think about it. This is a very, very general construction. Yeah? And the only two ingredients is an action and a notion of exact sequences. That's all you need. The action map. Yeah, yes, okay. So, yes. Okay, so that was in principle the final sentence. Now I will answer your question. And then we'll see tomorrow how to compute this. So we had this group action of GD on RD. Yeah, this was given by, let me remind you, GI on F alpha is defined as the GJF alpha GI inverse whenever you have an arrow alpha from I to J. That was the action such that the orbits are the equivalence classes. So this, you can say, is a map GD cross RD to RD. And this map I call action. Okay, so, and here I'm taking not the whole space, and I'm taking the quotient by a group. So here I take GD cross RD, but a quotient by some subgroup. Let me just call it GD prime. Yeah? And this action map is invariant under this diagonal action. Well, honestly, that's the anti-diagonal action. That's why it's invariant. So it factors here. And actually, then you can restrict the RD to some RD prime. And then we are there. Yeah? But the action map is essentially just this map, and then you just check that it is well defined on this level. Yeah. Okay, this is one ingredient. The other ingredient is upper triangular matrices, because these give exact sequences. Okay, thank you very much for your attention. Thank you. Sorry? This map here? No. Absolutely not. No, 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 no. It isn't. Uh-uh. Yeah, I will tell you an example that not even this action map, I mean that this action map restricted to here is not it's not subjective. Yeah, let me give you this example. Namely, in this classification of quiver representations, it might happen that you cannot transform a quiver representation into such an upper block form. Yeah, so this happens, for example. So an example, these are these really bad unclassifiable quivers. Yeah, so you take two loops, and let me take the matrix A to be lambda 0, 0 mu, where lambda is not equal to mu. So this is a diagonal matrix with different eigenvalues. And let me choose for B the flip of first and second basis vector, 0, 1, 1, 0. And then exercise is that you can't find an invertible matrix G in GL2 such that both GA G inverse and GB G inverse are in upper triangular block form. Yeah? And solution to the exercise in a word. What does it mean in upper triangular block form? This means you have a vector which is a common eigenvector for the matrix A and the matrix B. The matrix A has two eigenvectors, first and second coordinate vector, but these are permuted by the matrix B. So there's no common eigenvector. Yeah? So you cannot transform A and B simultaneously to this upper triangular block form. So you see that then this means that this action map from upper triangular matrices to here is not surjective. This is one of the things. Another question is whether it is surjective in cohomology, but we'll just do some calculations tomorrow and see what happens. Yes, you can. Okay. Oh, yeah, you can easily do it. It's a huge diagram. I would need two blackboards. Essentially, what you do is you work with 3 by 3 upper triangular block matrices, like this. And you can either view this as, it's wonderful to have all these colors. You can either view this as having this block extended by this block, or you can view it as this block extended by this block. And if you write a huge diagram, then indeed you can see that gives associativity. That's it. I mean, it really follows from the linear algebra on just two ways to view upper triangular 3 by 3 block matrices. Yeah. But actually doing it requires lots of notation. This is the first thing I will write down tomorrow because I haven't done it yet, that this indeed defines an associative algebra, and then we'll see how to compute in it. Perfect, thank you.